Most of the lecture will be me writing on my iPad, so this is my first time doing that, but I think it's good because the material could be really dense, and so if I have slides, it's going to go really quickly and it's really easy to get lost. So hopefully this will force me to go slow enough so that we could cover all the material. Before we go into course logistics, let me just start with a broad overview of what machine learning is. Can y'all hear me in the back? Okay, great. So there's three broad categories of machine learning, and the first, and by far the most popular category, is called supervised learning. And by the way, you can take notes, but these will all be posted on the class website, so don't feel pressure to. But supervised learning, where the goal is to make predictions from data. So that's kind of abstract. So let's look at a specific example. So, often when we are working with data, we want to predict specific numbers. So, typically in machine learning, we collect a data set and we can plot that data set. Sure. Yeah, let's shut that off. Does that help?
A little bit. Just a little bit.
Okay. Is this better or this?
This is better. Yeah.
This is better? Okay.
I'm sorry.
No, that's makes the class have a fun vibe to it. Okay, so predict from, okay, that would be bad. Predict from data. So let's say that we're trying to collect data on, and we're trying to build a model that's going to predict the inches of rainfall tomorrow, given the humidity today, something that's, people may do in weather forecasting. So you're going to collect a bunch of data on different days. And so the x-axis in this example would be the humidity as a percent. And the y-axis would be inches of rainfall tomorrow. And to build this predictive model, we first need to collect data. So each data point that we collect can be plotted on our plot like so. So each of these data points represents a different day where we have both the humidity that day as a percentage and the inches of rainfall the next day as inches. Any questions so far? Okay, cool. So what we do in machine learning is learn a shape of best fit for the data. That would be this blue curve here. So that given a new data point, let's say, so we have this data, we train our model, this blue curve is what we've learned. Now let's say that we want to predict what happens with 40% humidity. So we could put 40%, go up to the corresponding point in our learned curve, and get the prediction. So this 40% humidity is the input. By the way, this is, sorry about my handwriting. Let me know if you ever want me to rewrite something. Is that legible? Should I rewrite that? Okay. Okay, thank you. And this is the predicted value over there. And that's what a machine learning model is. Now, there's a lot of details about how the curve of best fit is learned, and we're going to cover that in this class. But conceptually, what a machine learning model is not too complex to understand. I mean, you already know about curves, and you're finding the curve that best fits the data. Any questions so far? Cool. Can anyone, well, okay, so this is a subcategory of supervised learning called regression. And the goal of regression is to predict a number, like inches of rainfall. Can anyone give me other examples of real world regression tasks?
House price to area,
So what's the input in that case?
the area, like the square meter of the, I don't know, how do you say that, property,
Hmm.
whatever,
And what's the model predicting?
the house price
Cool.
in dollars.
Any other examples?
So we're predicting something like, so instead of rain, so we're predicting something based on something else. So it could be predicting based on the rainfall the previous day.
Yeah. Yeah, but that would be called forecasting.
That would be, would that, okay.
So yes, and in fact, so in the real world, it's kind of simplistic to predict something from just one other variable. So what we tend to have in the real world for the complex models is, I'm gonna draw it down here actually. So I'm just gonna draw a 3-axis plot. So now we have 2 inputs, x1, x2, and the thing we're trying to predict. And a bunch of data points now in 3D space. I'm not a great artist either, so bear with me. But does this kind of look like 3D data? Imagine, we have points out here. So what we would learn in that case is
Can you change the color of the yellow? It's not.
The yellow doesn't work.
yellow doesn't work. Okay. Do you want me to rewrite it or is okay? So let's see. No more yellow. It's unfortunately a default one, but let's try purple. Okay, so examples. What was it? Oh yeah. Input to the model can be square feet of the house, as well as many other numbers. It doesn't have to be just one thing. And the output, the thing that's being predicted, is the house price. But as we were saying, it doesn't require only one input. You could have 2 inputs or 1,000 inputs or 1,000,000 inputs. And we will learn how to build machine learning models that work with a bunch of inputs. And so now we're learning a 3D curve of best fit. Something like that. And so we'll learn how to learn these complex shapes, which will be cool. Does anyone know how to draw this with 10 dimensions? No? Okay. Me neither, but it would be an interesting research problem.
Input variable, input variable adds dimension. So with a single input output, you've got 2-dimensional, but 2 inputs, you've got 3-dimensional.
Yeah, so in the case of regression, when we have 2 inputs, the plot ends up looking 3-dimensional because 2 of those dimensions are the inputs, the 3rd dimension's the output. But we'll see in the next type of supervised learning that that's not always how we draw things.
Question, hold on, the question, my question is through the whole. Are you asking us to draw a 3D plot with 3D code?
The homework doesn't ask anything like that.
That's kind of leading question 2 based on what you just said.
we'll get to question 2. So today's not going to cover anything with question 2 on the homework. So I'll go over the homework and class logistics in a bit, but today will just get us through the first question of the homework, and we won't be ready for the other questions until next week.
Okay, I was just trying to apply what this was to. Okay.
Yes, no, don't just look at question 1 for this stuff. This is just giving an overview of what machine learning can do, not how it works.
Okay. I'm
So,
sorry.
Oh, no
as, like,
worries.
new data points are received, like the curve will kind of adjust to it over time.
Yeah, so you can, if you get new data points, you could retrain the model, get a new curve, and use that for new data. We're actually not going to talk about how the machine learning model learns these curves until a few lectures later, because I think the best way pedagogically is to start with learning what machine learning models do, learn how to evaluate them given that you have a good model, and then we'll talk about the complexities of how it's learned, because it involves a lot of math. But if we build up to it, it won't seem like a lot of math by the time we're there. But yeah, so we'll cover that. Any final questions on regression? Okay, and we'll learn how regression is learned in a bit. So the next category is classification. This is another type of supervised learning. The goal of classification is to predict categories. So let's look at an example, just like before. Is this legible so far? Okay, cool. Okay. I'm very self-conscious about my handwriting, so I apologize. So in this case, both of our inputs, we're gonna have a 2-input model, and we're gonna have 1 axis for each of those inputs. And we're gonna have data points for 2 categories. Let's go with cancer and not cancer. I work in AI for healthcare, so I might be biased. If I do too many healthcare examples, please stop me. There's many other examples of where AI is used. But let's start with a healthcare one. So we can record 2 different properties of people and record whether they have cancer as red and no cancer as green, and plot where they fall with respect to the 2 medical measurements we make about them. These could be blood reading values, these can be the color of a potential tumor, the size of a potential tumor, any numerical value associated that might be associated with cancer. In the real world, it doesn't look this clean, but just to start us off so we know what classification is. So we plot the people, we color them by their diagnosis, and what the machine learning model does in this case is learn a separating boundary between the 2 groups. So that, let's say you get a new person and they fall here on the plot. What do y'all think we would predict this person as? Right, so predict as no cancer. And similarly, if we get someone falling here, we predict them to be in the cancer group. So that is essentially what classification is. Any questions on classification? Yes.
For like edge cases for that, like if you had trained an AI to do that, and then you got a data point very far away from either category, would it output the
Yeah, great question. We'll talk a bunch about edge cases, but maybe since you brought it up, one type of thing that happens and which we will learn how to deal with, and which is, I guess, important to bring up now, is in the real world, the data are not dispersed so cleanly. We might have this type of situation, which we will learn how to deal with. And in those cases, much more complex boundaries would be learned that might not even be right next to each other. So we'll learn how to automatically learn those types of scenarios as well. Yeah, in the back.
Does that have to do anything with that clustering analysis?
We will cover clustering analysis, so that's actually the next broad category we'll talk about. Any other questions on classification? Yes.
So if there was different features, it would be a different dimension. Like if a patient had different symptoms and you would want to classify them as cancer or cancer, would that be under or would the graph be have more different dimensions?
So you're saying if there's more than two things we're measuring? Yeah, so I guess the way to visualize it is if there's three things, imagine all these points are just in the room and the separating boundary is not a line anymore, but it might be a large sheet of paper that's dividing up the room. Beyond 3 dimensions, it gets really hard to visualize, but we will learn how to visualize those cases as well in this class. Yeah, in the back.
So is the classification model only used for discrete outputs?
Yes.
Is it always like a binary, or could you have multiple categories?
You could have multiple categories. So you could have a third category that has its own boundary as well. And we will learn how to do that as well. Yes.
And there needs to be like a finite number of categories, because when I saw classification, I thought of like image classification, where it could be like a whole bunch of different categories that it could be put in.
Yeah, so we will learn how to deal with thousands of categories that are being predicted as well. You do need to pre-specify how many categories in advance, but once you've pre-specified that your model is going to learn however many number of categories, then you can train it to do that. Great questions. Any other questions? So far, it sounds like everyone's getting really excited about the things we're going to learn. So that is great. Who's really excited right now about machine learning? Okay, cool. I mean, that's not bad for a very math-heavy, programming-heavy class. Can anyone give me other examples of classification?
So for a classification example, would it be like you classifying proteins into multiple classes based on what they do?
That is one, yeah. And that is a real-world classification research project and industry project. There are companies that do that as well. What else?
Fire Pokemon versus water Pokemon.
Nice, yes. Classify Pokemon. Let's not use classify. Let's say name the Pokemon from an image of the Pokemon. Very doable in machine learning. We'll learn how to do that in this class. Yes.
Maybe like a CAPTCHA thing of like identifying. Well, I guess.
CAPTCHAs are used to train these models. So nice thing.
Well, yeah, I mean like an AI that would identify the letters.
Oh, like auto CAPTCHA fill.
Sure.
Nice. CAPTCHA filler. Yeah.
And you did it for TSA, how they have like images of like X-ray scans of people's bags.
Mhm.
Do they use machine learning to like classify if it's hazardous or not?
Ah. Yeah. I don't know if they do, but that they probably should if they don't. And therefore they probably do because that sounds very doable with machine learning.
I think they do because certain things when they go through, it'll come up as red, like shapes.
Ah, right. We will learn how to do that. Okay, I think, is everyone clear on what classification is conceptually?
Would another example be you've got a bunch of different paintings and you're trying to classify the artist?
Yeah, you can do that as well.
That could be another one.
Yeah, let's add that. Classify artist. Okay, let's go to the next category. Unsupervised learning, which is, learning. So the goal of unsupervised learning is to learn patterns from data. And there's many different types of unsupervised learning subcategories that we will learn about, but the first one you tend to learn in a machine learning class is clustering, which I think was brought up a few minutes ago. So the goal of clustering, and we're going to draw an example for each of these. So here's another example where the two input variables take up each of the axes. So y-axis is not, it's not the y-axis. It's not a dependent variable. It's another input variable. And we're going to draw some points. And in this example, let's say that x1 is number of comedy movies that someone watches on Netflix, on their Netflix account, and the x2 is number, what's another genre? Drama movies. So the goal of of clustering, which is a type of unsupervised learning, is to automatically group or cluster the data points together so that you can, for example, recommend the same movies to the users in group A, same for group B, same for group C. There's a lot of high-paying jobs you can get with the skills you learn in this class. Can someone give me other examples of clustering in the real world?
Types of different chips, like Ruffles or Lay's, based off of, like, I guess, texture of potato.
Nice. Just gonna say food items. What else?
Like the YouTube recommendation, right?
Yeah. So recommender systems in general, which we'll have a whole class on how recommendation systems work. So you can go interview at Meta or Google or Netflix and show that you know how their algorithm works. Here's another meta one. You can have grades of students in a class, and to assign final letter grades, if you want to curve it, you can group students together and give these students A pluses, these students A's, and these students A minuses instead of doing an arbitrary grade cutoff. Who prefers this for grading in this class? No? Okay. It's probably going to be a worse grade without doing this, but that's okay. We've already voted. No, I'm just kidding. I won't. Okay. Next unsupervised learning method, anomaly detection. Can anyone guess what anomaly detection is from the name?
Outliers.
Yes, exactly. So outlier detection. Anomaly just means outlier. This is often used, for example, in fraud detection, where let's say X1, X2 are now properties of someone who does a lot of bank transactions, and their data usually looks like this nice sinusoid that's really noisy. And then all of a sudden, you get a transaction way down here, then the bank may think that this is fraud, or at least send a warning about it. Yes?
So what makes that transaction weird? Is it because it doesn't follow the pattern?
Uh,
Other criteria that has that.
right, I mean, this is a toy example, but yes, if you have general patterns that a user is following, then all of a sudden you have something that's way away, like far, is really deviates from that pattern, then there's a possibility that that's fraud, and it's worth alerting the user that that transaction happened. Maybe it's not fraud, but
Is there usually like some kind of standard deviation in which they would define whether this is a deviation that is concerning or not?
yeah, I mean, there's different ways of doing it, but something like that. Yeah.
Like, if the transaction was like in Great Britain and you haven't been traveling or something?
Yes.
Yeah.
Yeah.
Is machine learning able to predict that that's like a sine wave or cosine wave?
You can build a model that, given those data, can learn the sine wave from it as a regression task.
Like, what if you don't know that it should be a sine wave?
Yeah, you can. Well, it's a little harder, but neural networks can do it, and we will learn about neural networks in this class as well. Who's heard of deep learning and neural networks? Okay, so there's a whole class on it that y'all should definitely take as well, but we'll build up to that because those are the best performing models, and spend a few classes on deep learning as well. But so if you really enjoy this class, definitely take that class because those are the state-of-the-art methods. But those models have no problem learning whatever shape, regardless of what you think it is beforehand. Okay, final unsupervised learning category that we're gonna talk about today is dimensionality reduction. So, as we've alluded to many times now, oftentimes in the real world, data are in very, very high dimensions. We might record 10,000 properties, and each data point consists, therefore, of 10,000 dimensions. But let's look at an example in 3 dimensions, where we have some data points in 3D space. What dimensionality reduction allows us to do is to project the data points down into a low dimensional space such that the points that are close together in the high dimensional space are also close together in the low dimensional space. This can be really useful, for example, when you're handling DNA data that has 3 billion readings and you want to visualize which sequences are close together, which ones are far apart. You can reduce the dimension down to, say, 3D from 3 billion D and visualize whose genomes are close together. It's a simplified example, but that's where this becomes useful. So we're going to learn how to do that too. Everything I've talked about, we're going to learn about. So that's it for unsupervised learning. Any questions? Sure.
We talked about features and having more dimensions. You mentioned color in one of your examples, and I just had a question about mapping these kinds of features to numbers to actually get into a space. Are we going to learn about that? And then also, are we going to learn on how to optimally pick that, like map those features to numbers?
So we're gonna have a whole class on computer vision, and we're gonna learn how our image is represented. Actually, we're gonna talk a little bit about that today too, but how our image is represented as data, because no matter what type of data we have, we need to represent it as numbers so that we can learn functions that make predictions from those numbers. There's standards for colors specifically. Have you heard of RGB
Yeah.
before? Okay.
I guess my question was more on like when you had kind of like this cancer, no cancer example, the color of that might not be related to. I mean, I guess you could still map it in RG. You know, you can use the numbers, but I'm wondering if you use different numbers, will you get better results? If you say mixed up the numbers in a different way. Mapping. In the case where it was all mixed up here on this example on the bottom.
Mm-hmm.
If the X1 feature was just mixed up a little, the green clusters might appear together.
Yeah. Yes, we will talk about looking at linear combinations of features. And that actually goes hand in hand with the dimensionality reduction in a way. Any other questions? Okay. So the final category of machine learning, which is going to be the most abstract, but it's really popular today in robotics and self-driving vehicles, is reinforcement learning. Who's heard of reinforcement learning before? Not in a psychology sense. Okay. It's basically the same idea as in psychology. So we're going to start talking about modeling, where you have an agent, like a robot or a self-driving car, that acts in an environment. So it takes actions in an environment and gets rewards for taking those actions. And so the agent will start in a state. This is so abstract, so I apologize. Takes an action and then ends up in another state while receiving a reward, then takes another action, ends up in another state, etc. Now, the action can be a discrete category, or it can be a continuous number. The reward is usually a number. The state is usually represented as a collection of numbers. Think a vector or a matrix.
This is unsupervised?
This is reinforcement learning. So this is a third category.
Okay, it's just like, okay, so it's no longer you no longer have to be unsupervised.
Right. Yes. So dimensionality reduction was the last unsupervised category. Thanks for catching that. Reinforcement learning, whole third different category. Although supervised learning techniques are often used these days as part of reinforcement learning. So they kind of start going hand in hand. This is really abstract though, so don't worry about this reinforcement learning too much. We'll cover it in detail.
What does it say collection of?
Oh, of numbers. Like, for example, e.g. a vector or a matrix. Who is not familiar with what I mean when I say vector or matrix? Okay, cool. So we can maybe go faster through some stuff than I anticipated. So the goal of reinforcement learning, this is the last thing I'll say about it, is what we're learning in this case. There's different ways of doing it, but you're often learning a policy function, P, which takes as input the state, which is a vector or matrix, and the action, and which returns the probability of taking action A in state S. So there might be action, sorry, this is a lot to write. There might be action A1, action A2, and action A3 that you may want to take. And it will return a probability distribution over the possible actions to take, so that there's an 80% chance it'll take action 2, 10% chance it'll take action 1, 10% chance it'll take action 3. That's the goal of reinforcement learning. How it does that, we'll talk a lot about. Yeah?
Is the policy function has anything to do with the probability distribution function or the probability density function?
Yes, they're very related. We're going to talk a lot about probability distributions here. A lot of times, the goal of machine learning is to learn probability distributions over some discrete variables or continuous.
Well, that's the something function,
Oh, policy.
policy function.
Thank you. Let me write that clearly. Policy. Did my handwriting degrade too much? Okay. Any questions? So basically, this is what we're going to learn. We're going to learn a bunch of different methods within all these categories. Hopefully, what the goal of machine learning is pretty clear. The details of how it's learned is where all the fun mathematical tricks come in. But it all comes down to calculus, probability, and linear algebra. So now I thought it would be useful to have a little break and talk about course logistics, and then we'll continue. So this course, everything's on LaLima, but there's a course website which is linked on LaLima. It's publicly available, and what you can do is take a look at the homeworks, which the first 4 of which are already posted. So you can take a look at homework 1 and say, okay, this is homework 1. This is too hard. I don't want to take this class. Or this is super easy. This is going to be a breeze. I imagine, given y'all's background, it'll be the latter. But these are already posted. So there's 5 homeworks in the class. Homework 1, 2, 3, 4, already posted online. You can look at them now. Homework 5, I'm working on it. And the final project I'm working on. The grading is roughly 35% for homeworks. So not roughly, exactly 35% for homeworks, 7% each per homework. There's opportunity for extra credit within the homeworks. There's a midterm exam and a final exam. The midterm exam will be in class if I can figure out the chair situation. Otherwise, it'll be take home. Not as an incentive to come or not come to class. That's an hour and 15 minutes, mostly multiple choice, auto-graded on LaLima, open notes, but therefore the questions will be questions that you can't just look at the notes to answer. So it requires understanding the material beyond just looking at the notes and answering the multiple choice questions. As well as a final exam that will be of a similar format. And these will be very theoretical, but also practical. We'll also have a final project worth 25% of the grade, where you're going to take everything you learned and do your own machine learning project, where you take at least 3 of the concepts that we learned in class, apply it to any data set that you want, implement it, record the results, write up a short write-up on it, which will have an intro and methods and results and discussion and a bunch of plots evaluating your models that you build. But hopefully, AI and ML can be applied to every field, these days. It can be applied. I like it in healthcare, but it could be applied to social science. It's used in psychology. It's used in science. It's used in every big tech company, every small tech company. It's used all over the place. In music even. I like music as well. So music, I have not to get too much on a tangent, but I have this Furbo for my dog that records it, and they are doing computer vision on that, and as well as bark alerts. So even on those types of products, machine learning exists. So it's all over the place. So hopefully the final project's an opportunity to apply what we learn to whatever area you're interested in. In terms of how the homeworks look, the first few questions tend to be a little theoretical. So here, we'll go over this. We'll learn this stuff in the future. And then there's a final coding question, which is on Google Colab. Who's used Google Colab before? Or a Jupyter Notebook? Okay, so we'll have a class for those who haven't used that before, just going over Jupyter Notebooks as well as all the big Python machine learning libraries. So not only will we learn the theoretical skills, but we'll also learn the coding skills so that you can go out in the real world and do projects. So the goals of this class are to ultimately to get you to be able to be a machine learning engineer or do machine learning projects in your research or in whatever company you end up joining. So the coding parts of the homework will help you with that. They will be largely auto-graded. You're allowed to collaborate, but don't copy. Homework 2 is going to be a little different. It's all coding, and there's a little contest at the end where it's all about having the best performing model. So if you hit a certain, I think in previous iterations this was done as well, but if you hit a certain threshold of performance, you get the full credit. The top scoring submission gets 5 extra credit points out of 10. So that's like 3.5% of your grade. I should have thought that through before. But the second place will get 4 extra points. Third through fifth will get 3 extra points. 6th through 10th will get 2 extra points. And 11th through 15th will get 1 extra credit point. So hopefully that's generous. And yeah, so any questions about course logistics? Yeah.
Are there any differences between like the graduate and undergraduate, or is it all the same for everything?
Great question. Nope, same class. The reason, well, with one exception, the homeworks are exactly the same and the exams are exactly the same. The reason being that a lot of grad students are not coming from a computer science background, so there's not a reason to make it harder. And at the end of the day, machine learning's machine learning. But the final project requires a little bit more from grad students, just because grad students tend to do a researchy type of project, either for their master's thesis or in their PhD. So for the coding will be the same for the final project, but the write-up requirements for the final project will be a little bit more for grad students. That shouldn't be too bad. Any other questions on logistics? Okay, cool. I guess one other feature of the course website, so this is using Morea. Has anyone done a class with the Morea framework before? Okay, I don't think I fully figured it out, but I tried my best. And so the way the interface works is that there's different modules. So we'll have an intro to machine learning module where we cover how to do machine learning for the basic linear models. Then we'll have a module on Python coding for machine learning, a module on the fundamental learning algorithms, the one that you need for every data scientist interview. We'll cover a bunch of practical topics, and then we'll end with deep learning.
I don't understand what is this, like additional homework? What is this?
Oh, no. So these are, the homeworks are grouped into these modules. So there's one homework for each of these categories. But there's also readings associated with each of these. And so because machine learning is so ubiquitous, the source of learning doesn't have to be only these lectures. The content is so universal that if you really like, for example, to learn through reading, there's a few books. There's even this really nice picture book I highly recommend called StatQuest, Illustrated Guide to Machine Learning. Who's heard of this book before? Okay, highly, highly recommended. This was a professor who quit his job to make like ML education videos full time. But he does a really good job. He also has a really excellent YouTube channel. So if you prefer to be a visual learner, recommend that. If you are coming from a math-heavy background, there's also math-heavy versions of the course readings. And these are divided up for each module. And of course, there's coding tutorials for all the different coding things we'll learn in this class.
So I'm looking at the modules. How did you get to that page you are there with modules?
So if you click on any module, you'll have it's called readings, but it's really just resources.
Okay, resources.
Yeah.
I see.
How do you even get there in the first place?
So the course website's linked on Lalima on the front page.
Oh, okay, so in Lalima we can go to this page.
Mm-hmm.
Oh.
And all assignments will be turned in on Lalima.
Quick question.
Yeah.
So, with these modules, are you expected to need to read all of them?
No, you don't have to read any of them. You should, in theory, be able to do all the homeworks and answer all the exam questions and do the final project through just the lecture. But different people have different learning styles, and some people prefer visual, some people prefer audio, podcasts, some people prefer really math-heavy books, some people prefer like books that have a lot of text and little math. So depending on what you prefer, I tried to list all of those options on the course website. Yeah.
That blue date at the bottom under the homework, is that the due date? Is that when it's released?
Good question. I guess that's when it's released. So the due date's on the homework itself. And on the front page of the website, we have the due date kind of here. They technically are due on midnight the day before the class that they're listed as. 10% penalty for late per day. That's pretty standard, right? Y'all are gonna be like, it's 1%. Okay. So yeah, as we see the way the course is split up, today we're just doing an overview of machine learning, what we're going to learn, and then we'll talk about some of the fundamental learning algorithms, the first one or two ones that you learn for classification and regression. So we're gonna start with supervised learning. Then we'll go into Python coding of machine learning. That'll prepare you for homework 2. And then after all that, we'll finally get into how the model is actually learned, like the process of fitting a model to the data. So that's not actually gonna come till the end of this month. But bear with me because there's a pedagogical reason for doing that. And then after we understand how models are learned from the data, we'll cover a bunch of the most popular supervised learning techniques. So that'll take us through mid-February. Then we'll go into unsupervised learning. So we'll spend one day on general unsupervised learning, one day on dimensionality reduction. Then we'll cover recommendation systems, which is a nice practical application that combines many of the ideas that we talked about. We'll have a midterm review and in-course midterm exam. Then we'll move into deep learning, which is the best performing method on big data these days, so good to learn about. We'll learn about different types of neural networks. We'll learn how to code deep learning models using the two most popular frameworks, TensorFlow and PyTorch. And then we'll go into some more applications, natural language processing and computer vision. Those are the two biggest applications of machine learning. So natural language processing, how do you make predictions from text? And computer vision, how do you make predictions from images? We'll do one day on reinforcement learning because it's kind of advanced and there's a lot more stuff to talk about. Actually 1.5. And then we'll talk about some human factors, looking into how to make models fair, explainable, and private. And then we'll have project presentations, a course review, and a final exam. Yeah.
When you said that we would get into at the end of January, that we're gonna get into the learning, which class is that?
That is the gradient descent class. But yeah, it's going to be a very important class because up until now, next class we're going to talk about what are the models, what are some basic models. Then following class we're going to learn about what are the common ways to evaluate a model given that it's already been learned. And then we're going to talk about coding, then we're going to talk about some math background, and then finally get into gradient descent. But it's not going to make sense without covering all those things in advance. But it should work because just think that, okay, the model has been learned somehow. I don't know how yet. We're about to learn it. But here's all the things you can do with a model, and then we'll get into how it's learned. Yeah.
Are we going to cover self-supervised learning?
No, but I love that as a topic. I assume that the deep learning class would probably cover that.
Okay. I'm just wondering because I noticed you were missing it.
Yeah, no, I mean, I love that topic. I do a lot of research on self-supervised learning, but for an intro class, I don't think that I want to. Does anyone really want to learn about self-supervised? Anyway, if there's topics that y'all really want to learn about, we can swap some of these out, especially in the second half of the class. But I thought that these are ones that people typically want to learn about in a machine learning class, widely applicable to industry and to research, broadly speaking. But I'm open to changing it up a little if there's high demand. Okay, any other questions on logistics? Okay, well, let's get back into lecture. So we, let's see, do I want to do representing data first or the math behind this class? Let's do the math covered in this class. So the math covered in this class, which y'all already seem to know, include calculus, linear algebra, and probability. So why do we care about calculus in machine learning? Well, the reason is because we tend to optimize a model given its parameters, and we'll talk in detail in future classes about what model parameters are specifically, but this is the common symbol for model parameters, theta. So model, here actually, let me make this even more broad. Model parameters slash stuff the model learns. We'll make it much more specific. And for any choice of model parameters or configuration of the model that's learned, there's going to be a different error value for the model. That is the difference between what the model should have predicted and what it actually predicted. That is the difference between the true value and the predicted value. And there's usually a trade-off so that we, for different model parameters, we'll have a different error. This is often called a loss. If you've done machine learning before, you've probably heard of a loss function. We'll cover that in detail.
Loss is true value minus predicted value.
That is one possible loss function. But error, just think of it right now broadly without a specific formula as how badly our model did. So our goal is to minimize the error. Even just like thinking in English, it's good to have low error when we do things in general. So we don't know this error landscape in advance. If we knew that, we'd be done. We don't have to do any learning because we already know the error landscape. So we just go ahead and choose the model parameter that's the best. What we do know is, given a particular model parameter, what is the specific error going to be? Because given the model parameters, we can use that specific model to make predictions and measure the error. What calculus allows us to do is by taking the derivative of that point, that is the slope of the tangent line, we can know which direction to move in towards a local minimum. That is, which direction to move in so that we get closer to our desired value of the minimal loss. So this is the desired value. So it's a cool trick because even though we don't know the error landscape, we know which direction to move in or how to update the model parameters such that it will move closer towards the optimal parameter set. Yes?
Would it always, would the error graph always be like a parabola?
No. It's not always going to be convex. We'll cover all those details in the future. But oftentimes you engineer these loss functions so that they're differentiable and convex and all that. But we'll talk about that in detail. This is just kind of a high level. Don't worry about the details right now. I'm just motivating you why calculus is so important for machine learning without going through the specifics, which we will cover.
And this is only possible if you know the curve, right?
No. You don't. So you don't know. You know the error function, but you don't know all the values of it.
But how would you calculate like the derivative if you don't know like the actual?
You know the error function, so you know what the function is for the error, but you're not going to go in and calculate it for every possible parameter value. You're not going to sample everyone to figure out what's the best value. And these are usually so complex, there's not an analytical way to solve it. For very simple machine learning models, there's actually an analytical way to solve it where you can do algebra and get the exact optimal parameter.
Yeah, that's what I was thinking, because
Yeah.
the calculus way would be to like set derivative to
Yeah,
zero. Like,
we'll talk about that. That's called maximum likelihood estimate. We'll get there. But usually it's so complex that you can't do that, and you therefore need computational methods to try different values and slowly get towards the optimal one, because you can't just solve an equation to get there.
I think that's gradient descent.
Yes, and so we're gonna have a whole class on gradient descent. Okay, so we're getting into some details. I apologize. I'm just trying to motivate why we care. So that's why calculus matters. Why does linear algebra matter? Well, it's typical to represent data as matrices, where the rows are different data points, and the columns are features. It's a new vocab word, but these are the model inputs. And you have a bunch of numbers, etc. So I don't want to go into more detail than that. I'm just trying to motivate things. But because we represent our data as matrices and as vectors, naturally linear algebra is going to come into play. And we'll see exactly how in many of our classes. Finally, probability is important for many reasons, but one kind of high level reason is that oftentimes our model makes probabilistic predictions. So let's say we have our true value and our predicted value. And I'm starting to introduce notation here that's really common in machine learning. So let me point that out. This theta for model parameter, very common notation. So you'll see that in a lot of textbooks. This y hat is also very common notation, where y is the true value and y hat is the predicted value. And a lot of machine learning methods, let's say the true values are binary ones and zeros, they'll predict probabilities of being the one value. There's many other reasons why probability is important, but at a high level, we often don't predict categories as, well, think about it this way. This machine learning is all about learning functions, right? So can you think of a function that's going to output red or blue, or the output's going to be a string that says cancer? No, cancer. No, that doesn't work. So it should output a number, but ideally you want to know how confident the model is of each of those numbers. So if you represent it as a probability, then you can have a confidence score, and you can know how much you should predict the model's output. So that's why we care about probability, among many other reasons. Okay, any questions so far? And we'll cover this math as we go. So I know y'all have taken the class, but we'll review not how to differentiate things, but how, like not what the differentiation rules are, but what it means to differentiate something conceptually. With linear algebra, we'll cover eigenvalues, eigenvectors, maybe SVD, things you learn about in linear algebra, but not from a, figure out what the eigenvalues and eigenvectors are. Actually, a little bit of that, but mostly on a conceptual level, why do we care about eigenvalues and how does it apply to machine learning? And we'll learn that in a just-in-time manner. Same with probability, we'll review that.
So does that mean that we won't be having to do that kind of low-level math? We won't have to be doing the hardcore math?
Very little of it. I'm trying to minimize how much of that you have to do so that the learning to work ratio is pretty good. I don't want you to learn math again.
Does that mean we'll have computational tools to do the math for us, kind of thing?
I don't think any of the homeworks require you to actually take a derivative so I don't think you need to. Or if you have to find the eigenvalues, it's so simple and such a small toy example that it'll be pretty easy to do. And I'll work out examples in class, so every time you do the math, you can see similar examples. So yeah, I don't want to make this a unnecessarily difficult class. I just want you to learn how machine learning works. Okay, any other questions? Okay, today's a little bit slow, but we'll start picking up next time. One last thing I wanted to cover today is representing data. So computers represent data as numbers, often, zeros and ones. Machine learning models require data to be represented as numbers. You can't. So in supervised learning, we're learning an output, a function that given input data is making a prediction. So input data is represented as X, and output data is represented as y, we're learning functions here. So we need to be able to represent all the types of data that we work with, whether that's images or videos or text or genomes or whatever you're interested in. It needs to be represented as numbers so that we can learn functions that can make predictions from those numbers. So I just want to end today on giving you a few examples about how typically data tends to be represented. The simplest case is tabular data. Whoa, what happened to my pen? Tabular data. This would be, for example, in a CSV file slash, well, I shouldn't say slash to be precise. CSV files can be opened in Excel, etc. I'm not being super precise here, but CSV files are files that can be opened in Excel. So tabular data, as the name suggests, whoa, that is not a straight line. 1 second. I'm going to post these online, so I don't want it to be so messy. Okay, table, as you would see when you open Excel or Google Sheets or an open source version. And usually you'll have numbers of some sort. I'm just gonna do ... You get the idea. There's numbers in the spreadsheet where the rows represent different data points. Data points are the rows, and features, using that vocabulary word again, slash model inputs, the different variables that are used to predict, are the columns. So for example, let's say that the rows are user 1, user 2, etc. And the columns might be number of tweets per day. And this column here might be average length of tweet. And I don't know, what would be a fun thing to predict from Twitter? Bot.
Elon Musk go?
Sorry?
Oh, that's when will Elon Musk go away from Twitter?
Yeah. Is it, not is it, should the account be blocked? And that would be, a binary variable, so ones and zeros. So we might have data like that. And we could build a model that given those inputs, the X inputs make the prediction of Y. That's easy to represent. Another common image so images tend to be represented as matrices, and actually not just images, but your computer screen is a series of pixels that's represented as a matrix where each pixel has a different number that represents the color of that pixel. So in this example, you might have some numbers for the face, and zeros everywhere else. Etc. And we now have a numerical representation of an image that we can learn a function on. So the x would be the image and the output would be some y. Any questions on that concept? Okay, so now we're making predictions from images. The last one I want to talk about is text. Natural language processing, really common. So let's say you have a sentence like, I love ICS 435/635/data 435. I won't cover how it's done, but we will learn about ways to convert text into vector representations so that once you have it in that representation, you can then put that vector as input into a model and train a model to make the right predictions from that input type. So we're basically at time. Are there any questions about anything about this class? Okay, well, I don't want to start something new with 1 minute left, so see y'all next time.